Welcome everyone to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's presentation is part of our series on preparing for the next generation science standards, and tonight's focus is on the practice of engaging in argument from evidence. Our presenter this evening is Joe Krajcik. We also have Ted Willard from NSTA online with us. My name is Bryn Slate, and I will be moderating the program tonight, and Jeff Lehman is here to provide technical support. I'd like to remind everyone to visit the NSTA Learning Center, your online portal for over 10,000 resources for science educators. You'll discover in the Learning Center that over 3,500 of those resources are free, and that you can add them to your My Library section so that you can access them when it's convenient for you. The community forums are a great place to connect with other science teachers and discuss the issues that are pertinent to your classroom. Our online advisors are available to help you find the resources that you need. And of course, do check out our free tools that will help you organize your professional learning and reach your goals. It's all available by going to learningcenter.nsta.org. At this point, I'd like to turn it over to Ted Willard. Welcome, Ted.
Thanks, Bryn. Welcome, everybody. Happy to have so many folks here as we cruise into December. Somehow it's gotten to be already near the end of the year. We're going to go along here, and for those of you who have attended all of these web seminars so far, probably could talk through my slides better than I can. But I will just give a general description here of some of the basics so that we all can sort of start on the same page here before Joe begins his session. As we've got here, the standards are being done in cooperation between 4 organizations: the National Academies of Sciences that developed the framework, the practices were listed in the framework, and we'll talk more about those. NSTA, obviously. ACHIEVE, which is coordinating the development of standards, and AAAS, the American Association for the Advancement of Science. There's a 2-step process here, really, that we've got, that the framework was released by the academies back in 2011. We have the standards themselves currently underway here. ACHIEVE working with the states that are highlighted there in blue to develop the standards, and the standards then will drive assessments, curricula, instruction, and teacher development. One other note to make here about the states, that the states in blue, while they are involved in the development of them, they haven't yet committed to adopting those standards. They've promised to give it serious consideration. And the states that are in gray that aren't involved in the process, they too will have an option once the standards are released to adopt. So we'll all be interested to see how that comes together. There are 2 public drafts. The first draft was back in May 2012. The second draft is coming soon. I can be a little more specific about that now publicly. ACHIEVE has announced that they are going to release those in the first week of January 2013, although they still do promise that they will finish the entire work in the spring of 2013. So that we're taking that to mean, the end of March. And that the standards, though, are not out yet. So be keeping an eye out, and we will see them coming. The framework, as I mentioned, was released in 2011, in July. It was prepared by a committee of scientists and science educators, had a few Nobel laureates in that process. There are 3 dimensions in the framework that are described: scientific and engineering practices, which is going to be sort of one of the points of tonight's session and of this whole series we've been doing; cross-cutting concepts; and disciplinary core ideas. If you're interested in having a copy of the framework, and I hope you've already gone and looked for that and started to look at it, it's a really useful document. You can get a free PDF from it from the National Academies Press, or you can go to the NSTA Press store and order a print copy. So these are the scientific and engineering practices, the list of 8 that we're working on here. Tonight we're focusing on practice number 7, engaging in argument from evidence. I said that it's number 7, but there really isn't a specific order to all of these, as Joe will get into, I think, some tonight. The cross-cutting concepts, 7 of those pieces. And I do want to mention that we'll be doing a web seminar series this spring that will address these cross-cutting concepts. And then the disciplinary core ideas, what we're familiar with is life science, physical science, earth and space science, and also engineering and technology, something that hasn't always been considered part of science standards. And each of these sections have individual subsections and then down to individual learning goal statements of what are disciplinary core ideas, is the language that the standards use. So here is a description of a performance expectation. It's not necessarily one that exists in the standards, pulled from an earlier draft. This idea: construct and use models to explain that atoms combine to form new substances of varying complexity in terms of the number of atoms and repeating subunits. And so what this performance expectation does is combines a practice, a disciplinary core idea, and a cross-cutting concept together. So, for example, construct and use models to explain. That's in the area of developing and using models. Atoms combine to form new substances of varying complexity. That text in orange is an idea within the structure and properties of matter. And then this idea of repeating subunits fits into the idea of patterns as a cross-cutting concept. I'm going to point out that these performance expectations really are describing what is to be assessed at sort of an endpoint of instruction, what students are capable of. It's not meant to be specifically what has to go on in the classroom or specific objectives for a single lesson. And with that in place, I'll turn things over to Joe, and we'll get to hear about engaging arguments from evidence. Go for it, Joe.
Hi, everybody. I'm very pleased to be here. I hope you can hear me. And let me start by just telling you a little bit about myself. I'm not going to spend a lot on this slide, but I'm currently a professor of science education at Michigan State University. And I think the other part that's really important for you on this slide is that I did serve on the writing team for the framework. I was the lead writer for actually the physical science core ideas. And I am also currently serving as on the leadership team for Achieve in order to produce the standards. So I do have some experience in this area. But my goal tonight is to hopefully help you learn a little bit about what argument could look like in the classroom. In particular, I'd like to show you its relationship to other practices. And I'd like to discuss a little bit more. Ted went a little bit into the framework and the next generation of science standards, but I'd like to just go a little bit deeper into that area to show you how they actually all work together. And then I'm going to talk somewhat about supporting students in argumentation, and hopefully there'll be some nice examples that you could follow throughout this entire presentation. And I hope that you and I can have a little bit of ongoing conversation. This isn't the best media for doing this because I can't see your reaction, so I am looking forward to your responses to my polls and also the questions that you will answer. So this is our first poll, and I believe that Bryn takes it over from here.
Thanks, Joe. And everyone, your poll buttons are now active at the top of the participants window. We'd like to know your opinion on when should students use arguments. So do go ahead and submit your answer using the poll buttons to respond. If you joined us a little bit later and didn't get a chance to practice the poll buttons in our introduction, you'll find that the poll button is right below your own name at the top of the participants window. It is a button that has an A pictured on it, and if you hold your mouse over that, you'll have the chance to select the answer that you think is best, A through D. And it looks like we've got a lot of folks jumping right on that poll. We appreciate your quick responses. And we'll go ahead and lock our poll in just another moment here so that we can check out everyone's answer. And now the poll will be locked now. I'll publish that graph And then turn it back over to you, Joe, for a discussion of the results.
Well, it's interesting that everybody jumped on B. I'm actually pleased to see that. That's actually a nice little background to begin with, that indeed one of the reasons why we want our students to engage in arguments in our classroom is actually for them to defend their claims, but not only the claims they might make, but also some of the designs they might have for investigations, as well as their questions. So let's just go a little bit deeper into this area. So what does it mean to engage in arguments? So as in that previous slide, students engage in scientists engage in arguments to also defend their claims. But an important aspect of that is it's to use evidence and reasoning. So when we talk about scientific argumentation, what's critical is that students always need to defend their ideas with evidence and with reasoning. But beyond their claims, which we might want to define a claim as a statement that answers the questions, scientists often use evidence as well, argumentations to defend their models, as well as to critique the claims of other scientists. So when they do that, they often look for insufficient and inappropriate evidence. But besides looking at claims and models, scientists also use argument to defend the interpretation of their data, because other scientists, as we said in the previous slides, might critique their work. And one of the ways in which their work might get critiqued is by a misrepresentation of their data, or of their experimental design, or of their methods of data analysis, or perhaps even an inappropriate question. So scientists use arguments for a variety of different reasons. Overall, they want to basically support their claims, but indeed they use it for other aspects as well. This is a statement taking about argument from the next generation of science standards. And what it states, I'll just read it to you. In science, the production of knowledge is dependent on the process of reasoning from evidence that requires a scientist to justify a claim about the world. In response, other scientists attempt to identify the claim's weakness and limitations to obtain the best possible explanation. So in essence, this slide represents the process of science. What we're trying to do in science is always explain the world. We will want to make sure we have the best possible explanation, and we go about doing that through a process of argumentation. Does this explanation, is it the best possible explanation to really explain this phenomena? Do we have the right evidence? Do we have sufficient evidence? And so this is the process of what science is all about. And we've seen this in many respects throughout the history of science. We've seen this in the argument about where is the center of the world, or of the solar system. Is it the sun, or is it the earth? We've seen this in the history of chemistry with phlogiston theory, with Lavoisier and Priestley. We've seen this as time goes forward. We've seen this with the structure of DNA and what's the appropriate structure of what the DNA molecules. We've recently seen this in all the conversations related to, indeed, are we in global warming? So this process of trying to come up with the best explanation and using argument, i.e. do we have the best evidence, has gone on in the history of science. So one of the questions we might ask ourselves is, what's the difference between explanation and argumentation? And last week, you saw that Lee McCune and Kate McNeil talked about explanation. And explanation is literally the product of science. This is what we want to do. We want to explain what the world is all about. So as they said in one of their slides last week, explanation in science refers to the goal of science is the construction of theories that provide explanatory accounts of the world. A theory becomes accepted when it has multiple lines of empirical evidence and greater explanatory power of phenomena than previous theories. So that's explanation. Argumentation, on the other hand, is the process of defending those explanations by carefully ruling out other alternative explanations and building the case that the data collected is sufficient and appropriate to serve as evidence for the current claim. So arguments are all about the process of building our explanations. Explanations are the final products. So here's an example to walk you through this. And I have up here that this is a composite example. And the reason why it's a composite example is because it's made up from my history of being in the classrooms. My background is chemistry, so you'll see a lot of examples today that I'll pull on chemistry. And this is actually an example that I pulled from some composite experiences I've had in 6th grade classrooms. So the teacher begins class with the following question. So based on the experiment we did yesterday, is gas matter? And a student responds, I think gases matter. Now that's a claim. The claim is actually a response to the question. It's a statement that answers that question. So gases matter. The teacher follows up and says, why do you say that? What evidence do you have? The teacher is trying to provide some support, prompting the student for some evidence. Josh continues and says, because yesterday when we blew up the balloon and then weighed it, it weighed more than the empty balloon. So that means that gases that make up air have mass, and if something has mass, it must be matter. And because I could blow it up, it also took up space. So air has mass and volume, and it matters. So Josh now has provided evidence. He's made a claim. He's provided evidence. We don't have an argument yet. We just have Josh's claim and evidence. But Gemma quickly shot up her hand and said, I think it was a bad experiment. We used air from our lungs to blow up the balloon. Air from our lungs has water in it. You can even see the water droplets on the side of the balloon. Now what Gemma is providing is a counter-argument to what Josh has said. She's calling into question his experimental design. The teacher then asks, what do the rest of you think? So the teacher is trying to get more input from other students. Aubrey then stated, well, I agree with Gemma about the air from her lungs having moisture in them, but I also agree with Josh that air is matter. We should add air in another way. Another student, Dan, then answers, we could do an experiment and blow up our balloon using dry air. So what you see here is a counter-argument for a better design of an experiment. And as a result of this process, the class could, and so that was an argument. A person made a claim, he provided some evidence, we saw some students give some counter evidence against it, or attacking, and not attacking, but commenting on the design of the experiment. And here's what the final explanation that the class could actually end up with. So gases are matter because they have mass and take up space. That's a claim. Our evidence for this claim is that when we fill up containers like a volleyball with dry air, it was heavier than the empty ball, so it has mass. We could also put air into an empty ball, but eventually we could not add more air. So this showed it takes up space. So the above was our evidence, and then it says this showed it took up space. Matter is anything that has mass and occupies volume. Therefore, gases are matter as they have mass and they occupy volume. So we see a process of going from argument to explanation. Now this, I didn't want to just stop at sort of my composite experiences. This is now an example from an actual classroom. This is a group of 8th graders who undertook an investigation of population change. Students shared ideas to account for changes in populations of the Galapagos finches over time. And students discovered that during a drought, most of the birds died. And they wanted to attempt to explain why the birds died and why others survived. So the claim is, Kelly says, I think it's because the birds with the smaller beaks died, and the longer beaks were able to have children, and their children had longer beaks. So they survived, and that trait was being passed on a lot. So that's a claim. Now there's a challenge to the claim. Ina says, I don't think so, because we have this graph that shows that the wet season of 1973 to the dry season of 1978, and it jumped up. It wasn't that the ones with the shorter beaks died. Even the longest beaks here is like pretty much even with the middle of the pack in 1978. So we see Ina posing a counterclaim with some evidence. And I'd like to thank Iris Tabak and Brian Reiser for this example. So I believe I pass this on to Breen. Is that correct, Breen?
Thank you, Joe. And everyone, it is now time for our first question break. And before we get to that, I'd just like to remind you that you do have the option of turning off notifications of other participants joining us just by following the steps there on the screen. For Mac users, it won't be edit, it will be selecting Blackboard Collaborate at the top. You can also either minimize your chat panel in just a moment or detach and expand it to get a better view of the conversation. I'll also remind you that you are welcome to participate in the discussions there in our NSTA Learning Center community forums, and we welcome you to join that. I'll post the link there in the chat window. At this point, I'll turn on the chat and look forward to seeing your comments and questions. And I'll turn it over to Ted to present those to Joe.
Yes, thanks, Brandon. To start off with what I think is a really interesting question that Peter has asked here. He notes he's both an ELA teacher and a science teacher, and currently he's using a Common Core rubric for argument writing to assess the students' arguments for claims made for investigations. And he's interested in knowing, will there be a different science rubric for argument, or is it acceptable for now to continue doing this?
So Ted, I didn't quite hear all what you said, so I'm going to repeat it. I think he said he has a rubric, and he wanted to know if the rubric that he has is appropriate for argument as well as explanation. Is that correct?
What he noted here is that he's got a rubric that was developed for the Common Core and English Language Arts standards and how they talk about argumentation, and is interested to know if that same rubric would apply here to argumentation in science.
Yeah. So Peter, that's a really good point. I have not looked at those rubrics, but one of the things that I'm so excited about is how there is this integration and some commonality between the Common Core in English Language Arts and in mathematics. And so in both of those, what I know that from, at least for the world from language arts, that indeed they speak a lot about argument, and it's kids making claims and having reasoning and justifying, and having evidence and justifying that evidence. So if that's what your rubric says, then I think it's extremely very appropriate because in the exciting aspect, at least for me, as we move forward in the next generation of science standard, is because of these connections between the Common Core in language arts, mathematics, and then the next generation of science standards.
Great. I'm just going to throw a little bit up here as well, though. I'm going to post a link that has a Venn diagram that's making some comparison of the practices in science, math, and ELA that was been done by some folks, I think, over at Stanford. But I'll put that up in just a second. First, I'm going to go on to some other questions. So these examples highlight the statements of claim first, then supporting that claim with evidence and reasoning. And it ties in here again to Common Core ELA. They're emphasizing evidence-based writing in which we really need to build evidence first before we make a claim. Is there an important order in how this all comes together, Joe, or does it fit together? And if you want to push this off, because I know you're going to talk about claim evidence reasoning some more in a little bit, if you'd like to.
You know, I think that's a really good question, but I'd like to come back to that one at the end. So I missed who said that, but we're going to have a section at the end which we're going to talk about how to support kids in this process. And that will be a good time to address that. So it's jumping a little bit ahead, so I think I'd like to come back to that.
Great. I think we have a couple of other questions here, maybe a little bit appropriate later, but I do think we've got one here. You've noticed that scientists attempt to identify the weaknesses and limitations in an argument to obtain the best possible explanation. Obviously, if other scientists have evidence to support a claim, then an argument won't result. And I think this gets into that issue. If you can maybe talk about, what does argument really mean here?
So Ted, I once again missed part of your question. For some reason, you're dropping off on me.
I'm sorry. Let me try here again to repeat this question. You stated that other scientists attempt to identify the weaknesses and limitations to obtain the best possible explanation. Obviously, if other scientists have evidence to support a claim, then an argument won't result. And so this aspect of argument is often thought to engage in, a disagreement or two opposing thought processes here. And maybe you could talk a little bit about that issue.
So if I understand the question correctly, scientists always, when scientists make claims, they always have evidence. The question becomes, does new evidence surface that can better provide a better explanation, not only for that phenomena, but for more phenomena. And so as more evidence becomes available, then we often see how we understand the world as changing. So for instance, if you think back to the history of the atom, there was a time when there was, we knew that there was charges in the atom, but we took it as the electron sort of being stuck inside and around the atom, right? So this is sort of J.J. Thomson's model. But it fit the evidence of that day that there is positive and negative charges. But as we gathered more data, like for instance, throwing different kind of rays at a sheet of gold, and then it bounced back at us. So we said, oh, lot went through, but some got bounced back. How does that fit the model that we had before, that were these solid spheres? And so new evidence came into play. And so as new evidence came into play, we had to change our model of an atom of being this solid sphere, of rather being made up of this very tight, small nucleus surrounded with electrons. And so that basically composed of empty space. So often what happens is that when scientists propose an explanation for something, they feel pretty solid about their evidence. But as more evidence come into play, then we change what our claims are. I hope that helps make sense of that question. So it's not that, and often sometimes scientists also may misinterpret their data, right? Or they don't have enough data. And I think the last 20 years of do we have global warming or don't we have global warming, I think it actually is a really interesting case of people interpreting the data differently. And people saying, well, that's not really sufficient evidence to warrant the claim that you're trying to make. So this is both a case of some scientists saying, or some people saying, there isn't sufficient evidence, and other people, just saying that's not appropriate evidence. So we see these examples both in the history and science and also currently.
Yeah, I think two interesting comments here in the pieces here, and I will move on to your slides here. And Teresa's point that we might have to clarify when we use the term argument in science, we mean something different than an interpersonal disagreement. And then some points about a little bit, someone else was earlier talking about, do you have to have both a claim and a counterclaim in order for something to be considered an argument, two opposing points of view, or is it just is it an argument even when someone's just making their case for something, even if there's no one who's disagreeing with that? I think those are some interesting comments in place here that we can continue on as we move on through the next section.
That was actually some really interesting points. And I think often what you'll see in scientific publications and elsewhere is that people try to prevent people from raising the point. So they basically raise the objection and say why that isn't the case. And so you'll see this argument structure say, well, it can't be this because of this. So arguments tend to have that flavor. So we should probably move on. We have another poll. So in this case, the question becomes, what is the best reasons for students to engage in argument? And I think I popped this over to Bryn.
Thanks, Joe. And it looks like a lot of folks have already jumped on that poll question. Everyone, it is now active at the top of your participants window. And you can let us know what you think is the best reason for students to engage in argument. It'd be great to have everyone submit an answer on this one, and because it is based on your own opinion as a science teacher. So do choose a letter there on the poll buttons. We'll give just another few moments here for everyone to get their answer in. And it looks like we've got about 75% of responses in, which is pretty good. We'd love to have 100% response. If you're listening and have not yet chosen an answer on the poll button, please go ahead and do so now. And we'll go ahead and lock the poll button now and publish that graph to the whiteboard. And Joe, back to you to discuss these results.
So I did a little bit better as far as my assessment writing skills on this one. So we have a little bit more of a spread of results, but this one was a little bit different than that first question, because in some respects, all these answers could apply, right? We indeed do want to have students defend their ideas. This goes back to actually one of the comments that Ted just made, and it's not just we're trying to get kids to engage in controversy or kids just to disagree with each other. Argument in science is actually having students defend their ideas both with evidence and reasoning. And so that's the 2 points, both points A and C, that the reason why we want kids to engage in argument in science is because we just, in some respects, we don't want them to just know the science facts or the scientific theories or explanations. We want to be able to have them defend those ideas, and we want them to have them defend those ideas with evidence. And of course, that's what helps them really make sense of the world, because it's not just that they have the theory, they actually know why why in fact that theory exists. And in many respects, that's the whole process of actually engaging in the process of science. So this was an interesting question, because when I wrote it, I actually didn't want to have a sort of like a clear answer, because all these answers in some respects are very appropriate. So looking at the importance of arguments, this expands a little bit on what we just got done talking about. But arguments, in many respects, can help students really develop much deeper understanding of the content of science. In this case, I called it the disciplinary core ideas and the cross-cutting concepts, because it matches up with the framework and the next generation of science standards. But there's evidence in the literature, in the science education literature, that really supports this idea that when you actually have kids engage in this process, that it really helps them build a deeper understanding of important ideas of the science content. Using evidence to construct and critique arguments is also a very important 21st century skill. When our students go out in the workforce, this is what they're going to have to be able to do. They're going to have to be able to make claims, but they're going to actually have to be able to actually support those claims. So this is really an important process that's not only valuable for science, it's actually and important for their life no matter what field they go in. And in that respect, it really helps to promote literacy development. This was Peter's initial question regarding the rubrics with the Common Core and Language Arts, that if we can engage kids in this process, it's really going to promote not only their scientific understanding and not only their scientific literacy, but also their literacy development in general, because they're going to be able to know what makes a good argument. And this is going to be critical for them as they examine many, many claims that are made in the media as far as just about anything. What's a good product? What's good for my health? They're going to know to listen for evidence and for reasoning. And the last point about argument is important, is it really helps them understand what the nature of science, build a better understanding about the nature of science. So a question becomes, is this an isolated practice? I think, so the question I have up here is for us to guide the next couple of minutes of discussion is, where does argumentation fit into other scientific and engineering practices? Now, Ted showed you that list of scientific practices to begin with, and it was linear, although Ted said it's not a linear list. And one of the things I want you to recognize is that scientific practices are the multiple ways, and different scientists are going to do this somewhat differently, but it's the ways in which science explore and delve into understanding the world. So I have this little phrase here, the multiple ways of knowing and doing that scientists and engineers use to study the natural world and design world. But when doing it, they're not isolated a set of questions. So engaging in science is almost like a set of related practices. You're never going to isolate just argumentation from the rest of them. And that's the process that shows how science is really done. So I have a little, hopefully some slides that build here. So what you'll see here, these are the 8 practices that Ted pointed out in the beginning: asking questions, developing and using models, planning and carrying out investigations, analyzing and interpreting data, using mathematical and computational thinking, developing explanations, engaging in argument, and obtaining and evaluating and communicating information. But these 8 aren't necessarily linear, nor are they isolated. In fact, they work together. Now we may start, and there's other ways of doing this, but we could start by asking a question or defining a problem. But often when we ask a question and define a problem, that leads to, how am I going to find this out? That leads to planning and carrying out investigations. That could lead, if we actually collected data, to analyzing and interpreting data. Now, just to give you another sense here, it could have actually went from, I don't know if I can grab something. It could actually go from planning, carrying out, to obtaining information, right? So it's not, this isn't the only way this could go. I could have planned out and carried out my investigation and said, oh, I gotta obtain some other information. But let's just say I planned and carried out some investigations, and that led me then to want to analyze and interpret my data. Of course, that could lead to using mathematical and computational thinking that pushes me back to further analyze and interpret my data. That could lead me to actually engage in an argument from my evidence, which might lead me to develop a model, because a model is more of a holistic sense of what can explain a host of phenomena. That could actually lead me to really developing a really solid explanation, which might lead me back to actually asking more questions. So this is not, these things are intertwined together, and doing one process actually leads you to doing another. And I tried to give you one example of how things might be connected. But they could be connected in other ways. This isn't the only way that these could be connected. I might, for instance, be, just, for instance, I could start by looking at some information. And that could actually drive my asking questions. So what we're going to do now is back up and just think a little bit about the next generation of science standards. So see how those 3 dimensions that Ted mentioned initially at the beginning and how they all fit together. So one of the things that the standard says, the framework very clearly points out, is that standards have to emphasize all 3 of those dimensions: the cross-cutting concepts, the disciplinary core ideas, and the engineering and scientific practices. And what comes from that is the notion of performance expectations. And what performance expectations really do is specify how kids should make use of that knowledge in terms of a performance. So that's one of the major differences that actually exist in this version of that came out of the framework, that we want to have standards actually specifying how kids should use knowledge. And one of the ways they could use knowledge, of course, is in terms of arguments. But it's not the only way. They could make use of it by applying many of the other practices. So here, what I have in front of you is an example of how these performance expectations, which will be the next generation of standards, have actually been developed. So you can, in some respects, you can start with a cross-cutting. You can start with a core idea, which is you'll see on the left side of your screen right there. This is, in fact, a core idea taking from the grade band endpoint for the nature of matter, and it literally talks about that all substances are made up of atoms, and that these atoms form molecules, and of course there's liquids and gases, etc. And the way you get these performance expectations is you cross them, you might say, I like to use the word cross, with a cross-cutting concept. In this case, it's patterns. And of course, since today we're talking about arguments, I'm crossing it with the practice of constructing arguments using evidence. And when you do that, you end up with a performance expectation. And like Ted's case, this is a made-up performance expectation. But it says it's not actually one of the ones in the standards, but it's close. Construct an argument to defend the claim that the motion of molecules changes as the temperature increases. So we see a blend of making use of a practice, which is how we want the students, that's the performance that I want the kids to be able to do, and it's crossed with the core idea. And of course, the pattern in this particular case is almost it's assumed, because the only way we could actually, this happens, is because this is a pattern that always occurs when the temperature changes. And here are some performance expectations using examples of performance expectations. These have been modified for the purposes of this presentation, but they go across both elementary, middle school, and high school. So I'll look closely at the elementary one here. Construct an argument using evidence to support a claim about the relationship between the change in motion and the change in energy of an object. So once again, we see this blend of a practice with a core idea, and that's knowledge and use. And so you can, when the standards are released, or when the next version's released, or if you looked at these previously, you'll see that all these are written in terms of this fashion, that we want kids to be able to make use of the core ideas with a particular practice. So I certainly want you to come away from this session with a much richer understanding of argument. But if you come away with one idea, another idea, this is the one I want you to come away with, is that in the future, or hopefully in the past, we can't treat content and inquiry separately. These things are actually integrally linked together to help kids form knowledge or form understanding. And I like this analogy of this rope, because when we use this analogy of a rope, it symbolizes that it's much stronger than just one of these single strands. So we really want to have kids who can develop understanding that's really rich and that they can apply in their daily lives to solve problems. We have to get them involved in using these practices and arguments blended with the cross-cutting concepts and the core idea. And that's a very different approach to what we've done previously in classrooms. Often, and unfortunately, in some respects, our focus has been here on, here on core ideas, and not on this blending of the three together. So, as we move forward in our teaching, we have to actually blend these three things together. In this case of argument, it's when kids make claims, we have to always, as a teacher, say, what's your evidence for that? What's your reasoning? Are there other possible explanations? So the standard also make use of this other really powerful idea, and that learning just doesn't happen in isolation. Learning actually happens over time as students construct and rework ideas. And I mention that is because if we really want kids to develop this rich understanding of argument, it has to be done over time. It has to start, this is not just for the high school students, this is as much for the kids in first grade, in fourth grade, in seventh grade, as it is for kids in high school. That we all have to work together through the years to actually help them develop much richer understanding. And so this idea of learning develops over time is that kids will form much deeper understanding as we get them involved in these tasks, like using arguments that force them actually to say, what's my evidence and what's my reasoning for this? And of course, this last bullet that I have on this slide, it says developing this understanding is dependent on instruction. This isn't just going to happen. It really depends on what you and what we do in our classrooms. And that goes just as much for me as it does for you. Since I'm responsible for helping develop future teachers, I certainly have to provide them with that kind of instruction as well. So here's just an example of what this designing instruction might look like over time. You can see kids in second grade might make a claim and use evidence. As they get a little bit older, they can certainly construct scientific evidence, drawing on evidence or a model, but also taking into consideration other ideas. Does this fit all ideas out there? As kids perhaps progress to middle school, they can certainly present both oral and written arguments. Again, this is really supporting a lot of their literacy skills. But again, supporting those arguments by empirical evidence and reasoning, and then refuting other possible explanations. And then in high school, we certainly want kids to begin to bring up counter-arguments based upon evidence and challenging other possible proposed arguments. So this, in fact, this is what we would hope to see all students who graduate from our schools be able to do with respect to arguments. This is actually part taken directly from the framework document, and what all kids who leave our schools should be able to do, which is construct a scientific argument showing how the data support a claim, identify possible weaknesses in scientific arguments of other scientific arguments using appropriate level of knowledge and evidence, identify flaws in their own arguments and be able to modify those their own arguments in response to criticisms, recognize that the major features of arguments are this claim, data, and reasoning, and distinguishing these elements and examples, and of course being able to apply this stuff as they read media reports. And now it's time for another bit of interaction between us.
Thank you, Joe. And everyone, I'd like to remind you before we do get to our question period that you do have the option to set your preferences, and this will be reviewed for most of you who have been with us for the entire session, but just so we can recap these options for you. Also, we encourage you to check out the NSTA Learning Center community forums. I'll again post that link there in the chat window for you to click on and bookmark to access later. We'll go ahead and get on to the question period. I have now opened up the chat, and we look forward to seeing your questions and comments. And over to you, Ted.
Thanks very much. I'm going to start with actually a question that was sort of left over from the last set of questions here. But how can you best explain to middle school students what evidence is so that they can engage in arguments? It seems to be a difficult concept for middle school students.
Great question. So evidence, at least in the way I've been using it today, is data. But it's not just data, because there can be a lot of data that doesn't necessarily serve as evidence to support your claim. So one form of evidence could certainly be data that's actually supports the claim that you make. So that's referred to, my colleague, I've done a lot of this work with Kate McNeil, by the way, who was the presenter last week, and Kate and I like to call that appropriate evidence. So often, one of the challenges that we have as teachers is that students might use data, but it's the wrong data. In fact, it's not just students. We see this a lot with adults. They're trying to support a claim, and they actually use the wrong data. So one of the things we want to make sure we look for is appropriate data. The other aspect behind data is that is it sufficient? Do we have enough? And so we have to look is, have we provided sufficient evidence to support this claim? So in some respects, evidence is data that appropriately actually links to the claim, and you have to do that through reasoning using scientific principles often. And we want to make sure we have enough. But often if you're doing an argument, you could pull from other sources too. Like, for instance, you could pull from some theoretical ideas to support your claims. And when you look often at the journals, if you look at journal articles and you look at what scientists actually write, they actually use a lot of ideas from the literature in building their case. So those you may want to think of those ideas from the literature as also evidence, but you're basically trying to build a case both using these ideas from the literature as well as the appropriate data that actually fits your case to actually make it more solid.
Great, thanks. I like the comment that Pam Auburn gave here. I think of evidence as data in context. Moving on to a question from Terry. I know that NGSS will be performance expectations, but how is that different from learning objectives?
Well, learning objectives, I think, can take on a whole realm of verbs that you could use, right? So you might say we want kids to be able to recall X, Y, or Z, and the performance expectations that are in the standards are limited only to the 8 practices. So you will see when they come out that kids will argue, blah, blah, blah. Students will be able to construct models using evidence. Students will design investigations. So it's only limited to those 8, where objectives, behavioral objectives, actually can be a range of different kind of verbs that are in there.
Great, thanks. Andrew has, I think, an interesting question, something I've struggled with, I know. It seems like there's an overlap between models, explanation, and arguments. In what ways are they similar, and what ways are they different?
Yeah, great question. That's absolutely true. And I have to tell you, as a researcher in this area, along with my colleagues, I can name lots of them, these are things that we struggle with a lot. They're not necessarily clean cut. And one of the things I tried to do tonight was to give you, and I don't like to make things black and white, but I often, from an instructional standpoint, I like to do a little bit of that. So I tried to say that an explanation is sort of the thing we end up with, right? It's after the argument is done, and perhaps the argument will never be done because someone also brings some evidence in later and the argument starts over again. But at the end, we write this explanation. But the process of actually building that explanation was the process of argument. So the end thing you look at as the explanation, the process of actually getting there and saying, what's my counterclaim, and can I refute that counterclaim, and what's my evidence, all that is the argument. So a model. Models are also an interesting point to bring into this, because what explanations in some respects might explain one particular type of phenomena, whereas a model would actually explain a host of related phenomena. So that's the difference. So for instance, I might use the particle model to explain why something melts. But the particle model actually explains more than just melting, right? So you could have an explanation about melting, but the particle model, it's a model because it not only explains melting, it also explains evaporation and explains boiling. So it explains a number of related phenomena. That's the difference. If I just want to explain why this thing is melting, well, that could be an explanation. When I'm explaining that host of phenomena, then we're getting to the realm of models.
Great. You're reminding me of that a comment. I don't remember if it was one you had used or Stephen Pruitt. Someone has used this analogy being practices and tools, and the idea that a carpenter or someone building a house thing isn't just to find today we're going to use this tool and tomorrow we're going to use that tool. Is that you're frequently using combinations of tools together in all these things. So even though we have got these different practices in place here, at a given point in the classroom, students may be using several tools at the same time, several practices at the same time.
I totally agree. I totally agree with that, Ted. That's why I tried to show that list of the two columns of the practices, but showing that they're not isolated, right? If you ask a question, that could lead to wanting to find out some information. It could lead to designing an investigation, right? So it could then lead to kids actually thinking about, well, how am I going to actually analyze this tool and use some mathematical and computational thinking. So these things are not separated, and I don't want you to leave here tonight thinking that indeed argumentation is something separate from the other practices. In fact, you're not going to take part in argumentation unless you have a question to begin with and you have data to support it. So these things are integrally related to one another.
Great. I mean, we've got a few other good questions here, but I think if we could have you talk a little bit about your claims, evidence, reason, and some of the questions may ultimately fit into that piece. So why don't we move on from here?
Okay, so we're moving on. So we're now to another poll, and in this poll, this is actually supporting students. So now I'm actually going to, with this slide, with the next couple of series of slides, I'm going to be able to link back to actually one of their earlier questions. But we're going to first take a poll, and it says here, what do you think will be the most challenging about incorporating argumentation in your teaching? And A, having students use evidence, and B, providing alternative explanations, and C, being respectful of other students' idea, and D, supporting students in writing argumentations. What do you think you'll find the hardest?
I see that we already have lots of folks jumping on this poll and submitting their answers, which is great. I'll remind everyone that your poll buttons are located at the top of your participants window. The button is pictured with an A on it, but if you hold your mouse over that button, you will be able to select the appropriate response for you. And this is one that everyone should feel certain of an answer since it's based on your own experience as a teacher. So whatever you feel is most appropriate, do feel free to share that with us by responding to the poll. It looks like most folks have answered, so I'll go ahead and lock that poll now and publish our graph to the whiteboard so that everyone can take a look at those details. And Joe, I'll turn it back over to you for a discussion of the results.
Right. So as Bryn said, this actually is something from what you think you're going to have the most challenge with, right? So there isn't a most appropriate answer for this one. It's really what you think is going to be challenging. In fact, all four of these are actually very, very challenging. Getting students really to use evidence, particularly to use, as I mentioned before, sufficient and appropriate evidence, getting kids actually to take in alternative explanations, like what are some possible counter arguments of this, is really hard to do. You know, I think we've all experienced this in our daily lives and in our classrooms, that once people start to take a claim, they don't necessarily want to give that position up, and people will fight for it. And that's also true within the history of science. And certainly getting kids to be respectful. I think, Ted, one of the comments we heard before was, you know, arguments isn't about just disagreeing. And that's not what we want to have kids happen in our classroom. We don't want just kids to disagree with each other and not be respectful of each other's points of view. We really do want them to be respectful and listen very closely. And of course, to get kids to write arguments, that's a really challenging form of writing. So these are all very challenging, and hopefully within the next couple of slides, I'll give you some support in how you might be able to help students in this fashion. So we just basically got done saying this, so I'll just repeat this one really quickly. Student challenges is using evidence to support their ideas. We don't want them just to rely only on their opinion. Explaining why their evidence supports their ideas is also very challenging to kids. They can have difficulty articulating the links or using scientific principles actually to show why the evidence that they're using is indeed appropriate evidence. Often, as I said before, they want to focus just on one idea, so they're not considering alternative claims. Revising your arguments, again, getting kids to go back and look at new evidence and say, how might I change this? And certainly listening to what others say and taking their points of view into consideration. These are all aspects that students find very, very challenging within the classroom. And so here are some ways in which you might support kids in this process. And the first one is providing them with a framework. I'm not going to be able to go over all these, but I'm going to try to go over most of these. But so I'll read these quickly through and then pick on a couple to focus on. The first one is providing a framework. What do you really expect kids to do? And I'll talk about some pitfalls of that as well. You want to, in some respects, provide a model and describe that framework. You want to provide them with examples. You want to let them know why it's important. Fifth, why is it important to engage in argument? 5, have them critique each other's written arguments. Allow them to actually debate ideas in school, in the classroom, and provide them with various scaffolds. So I'm going to now go into these in some depth. So the first one was actually present them with a framework. And I think now for the last 12 years, I've been working with Kate McNeil in this process of claim evidence and reasoning. We've expanded it, of course, to go beyond just explanation and actually to take into consider counterclaims and rebuttals. And a claim is always a statement about a question or some problem. Evidence, as I said, is the data that is appropriate and sufficient to support that claim. And the reasoning is a justification that shows why that data counts as evidence to support the claim and includes appropriate scientific principles. The counterclaim describes other possible claims, like, well, it could be this, but maybe, maybe it's not. The rebuttals are, if someone gives you a counterclaim, the rebuttal is it provides counter evidence and reasoning why that alternative or counterclaim is not appropriate. So these in some, you can think in some respects are things that go into writing, taking part in argument. But one of the things I want to warn you about is we don't want to make this into a fill in the blank or a rubric in some respects, and give this process and not have kids realize that this in some respects is very dynamic and flows together. In the beginning, to have kids really realize that what's a claim, we actually want to talk about it as answering a question. We want to help them understand what evidence is. But in the end, we want to avoid this sort of lockstep procedure in the way I have it framed here. So we don't want to make this into an algorithmic formula, because then that destroys what argumentation is really all about. On the other hand, as teachers, we do want to help them understand what these various parts are. So this is an example of modeling and describing the framework. One way that actually works very nicely is actually by using common examples. And so here's a common example. This is actually an actual example from a classroom teacher. And the teacher says, so if I say Brett Favre is the best quarterback that, she loves Brett Favre, by the way, as a quarterback, she says, if Brett Favre is the best quarterback that ever lived, if I made that claim, what is that an answer to? And the student says, who's the best quarterback? So she's trying to get the kids to realize that claims respond to questions. And the teacher says, yeah, who's the best quarterback? So I think Brett Favre is the best quarterback that ever lived. The teacher goes on, so if I'm going to make a claim, such as the one I did with about Brett Favre, what would you have to say to me? And Sean said, well, that's just an opinion. Well, which it is. But the teacher says, that's an opinion. Well, what else would you want to know from me to support that claim? And a number of students said, the facts, the data. And the teacher says, yeah, right, facts and data, not necessarily opinions. So if I'm going to back up with facts or data, what do you call that? And then the kids go on and say, well, that's evidence. So often modeling and providing examples, common examples initially on, can really help kids understand what this framework might look like. And I'd like to just thank Ann Novak for that example. Ann's a teacher in Ann Arbor, Michigan. So one of the other things we really want to do is allow kids to debate ideas. And in order to do that in our classroom, we actually have to give our kids permission to disagree. Often a lot of the students who are in front of us come from cultures and backgrounds that it's inappropriate to disagree, particularly in a formal setting like a classroom. So we have to help our kids understand that, this is science class, and in science class, all students have a voice about, is this the best claim? Because in here, what we're going to do is we're going to raise questions, and we're going to look for what's the evidence. So we want to try to we have to give our kids permission. And you have to do that as a teacher. If we don't give them permission, we're not going to see this kind of argumentation happen in our classroom. And of course, if we do that, that's establishing a norm. But we also have to establish norms for acceptable behavior. And of course, one of the things is it's not that it's just my opinion or it's Joe that's saying this because Joe's the bright guy in the classroom. It's whoever makes a claim has to use it, has to provide evidence and reasoning and justification for their claims. And part of that norm building is not ever to allow kids to put other students down, because that's going to just shut certain kids up, and it's probably going to make quiet the kids that you don't want to have quiet. We want all kids to participate in this. So this norm of respecting each other is critical. And that one of those ideas are putting ideas down, and also getting kids not to talk when someone else is talking. These are important norms that if you really want to have this process of argumentation happen in your classroom, you have to help your kids realize. And of course, part of all this is really helping kids learn to listen, because it's just not natural, right? We want to get our ideas. We don't want to listen to what Jackie has to say or what Sam has to say. We want to sort of just get out our ideas. So we have to help kids listen. And there are techniques that we can do that. You know, we could do stuff like, oh, my idea is similar to Jessica's idea because, oh, my idea is different from Ann's idea because, right? So there's certain little helpful techniques that we can actually use to get kids to actually try and listen to one another. Another example that we can do, and of course what I tried to do just there was give you some scaffolds. Scaffolds are supports that can help kids do things that they normally can't do. And they're called scaffolds because often we want to remove those scaffolds. But in the beginning, when we're actually working with kids, we want to provide them with scaffolds. So here's a variety of different questions that we could use hopefully early on, and hopefully we can fade these as time goes on. But as teachers, we could, when a student makes a claim, what evidence do you have? Why do you agree or disagree? What are your reasons? What is your evidence? What could be some other possible claims? Do you have evidence for that other possible claim? Do you agree with the points being made? Why? Who has a different opinion? Why are you using that as evidence and not other data? How would your claim change if you used all the data? Does that make a difference? How is your idea related to what was previously discussed? What reasons do you have for saying that? So as a teacher, particularly early on as we try to engage our kids in this dialogical discourse in our classroom, we have to provide these supports, because if we don't, then we're not going to see this kind of give and take that we want kids actually to be able to do in our classes. So I'm just going to back up a little bit. There was one a bullet that I don't have a slide for, but I do want to talk about it just for a second, and that is that we really want to explain to kids why we're doing this. And in fact, Kate and I have some really interesting data that as teachers, if we don't provide a rationale for why we're doing this, and we do more of a, just have them do claim evidence and reasoning more kind of as a procedural type of things, kids actually do worse on tests, on achievement tests than they do if we provide reasoning for why we're doing this and using some of these scaffolds. So again, some of the reasons why we're doing this is because we really want to try to figure out what's the best possible explanation. This is what actually scientists do. So we want to always try to reinforce those ideas as well. Okay, so this is my dream, and this is kind of the thought another thought I want to leave you with, and that is, what would happen? Remember I talked about this notion of learning goes across time. And so my dream is, what would actually happen that if kids from grade 2nd to high school actually engaged in this process? Now, students of all ages and backgrounds can really take part in argumentation. And this is, so we have to have it be seen in grades K to 2, grades 3 to 5, middle school and high school. And you know, my big hypothesis, my big prediction is that if we start off in first and second kindergarten, having kids realizing, oh, I just made a claim, and then I need evidence for that claim. By the time, and we continue to build on that, so it gets more and more sophisticated, greater sophistications of, I'm making claims, and what's my evidence, and are there counter ideas of this, and what possible rebuttals might I use on top of that? You're going to end up with a very different kind of learner than we currently have in our schools right now. The kind of learner who can actually solve many of the problems that exist in our society. And I know many of you will say, can little kids really take part in argumentation? Well, here's an example from a 2nd grade classroom. So this is, and they're studying the behavior of mealworms. I'm sure many of you who are elementary teachers out there recognize this mealworm activity. And so the teacher says, okay, guinea pigs need water and get water from the water bottle. Do you think mealworms need water too? Now Sessa says, no, they don't need water. That's a claim. Kids can always make claims in some respects. No, but the teacher wants to provides the supports and wants him or her to actually provide a little bit more evidence. So she says, why do you say that? She's pressing for evidence and for further clarification. The student says, they don't have any water in there. Another student, Heaven, says, yes, they do. All living things need water to drink, or else they die. That's a counterclaim to the previous claim. And the teacher, again, trying to prompt for more evidence and for further explanation, says, Heaven, say more about that. And Heaven says, well, animals and plants die without water. There was this plant that we had, and it didn't get water for a while and died. If our mealworms didn't have water already, they would all be dead. So Heaven, going back to what counts as evidence, she's actually brought in some evidence here. This is a nice example of what evidence is and reasoning. And Charlie says, there is no, so now Charlie, notice what's going on here. Heaven actually provided evidence and reasoning to refute someone else's claim. Charlie comes back and now provides another counterclaim and says, there is no water in there. Where did they get the water? And the teacher says, providing, again, trying to provide some framework, who has an idea? And where can the mealworms get water from? She's trying to prompt evidence and further clarification. And Kurt says, they didn't have water in the container, but they do. But they have to have water. Maybe they got the water. They got it in the carrot. They eat the carrot, but they can get water too. They can get the water in the juices. So Kurt is now providing evidence to support the counterclaim. And Lilia says, there's juice in carrot. Juice is kind of like water. It's like a different type of water. That is where they get their water, in the carrot. So this is more evidence to support the counterclaim. And this is actually from I forgot to mention that this is from a second grade class. I said that. But this is actually from a class of very diverse students. And I actually want to thank Emily Miller for this example. Going up a little higher, this is now an example of a written explanation, because we not only want kids to voice these ideas in class, we also want them to write arguments. This is from a 7th grade class exploring water quality, and it says, so kids' response is, our stream is somewhat healthy, with a standard between good and fair, and can support some organisms but not all. That's his claim. My partner thought that the reason that the conductivity levels might be so bad, then there was some evidence, and I can't go into all the evidence because we don't have enough time, so it just says students provide evidence. But then he says, my partner thought that the reasons why the conductivity levels might be so bad is that there might be leftover salt from last year. His partner made a counterclaim. He's writing all this, by the way. And it says, well, I don't have any solid evidence to contradict this theory. I do have critical thinking on my side. We were told that in previous years of testing, the results were much, much worse because it had already snowed and salt had already been put down on the parking lots. Since this year the levels were down so much because of lack of salt, that makes me believe that any salt that may be left over isn't sufficient to affect that much. Because if the salt really was affecting it drastically, we'd probably be getting closer results to what other testers have gotten in previous year. So he's trying to provide reasoning to support the counterclaim. And I'd like to thank Ann Novak and her students for this example. So in conclusion, I'm going to just go back to this big idea. It would be great if all the teachers that were on this list, I don't know how many we have over 100, we all started, even with the very little ones, all the way up to high school, getting them involved in this process of actually building arguments and refuting claims with evidence and reasoning, because we'd have this different kind of learner. So it's important to help build the structure of argumentation, which really brings in many of the other kind of practices, because all learners can actually engage in this practice of argumentation. There's some of my contact information if you want it. I'm a fairly good emailer, krajcik@msu.edu. If you want to check out my website of my institute, it's right there at MSU. And with that, I think we go on to another set of discussion questions, right, Brenda?
Well, actually, Joe,
In the interest of time, we're going to hold that question break until after the evaluation. We're going to go ahead and go to Ted Willard's closing on resources from the NSTA website.
Great, thanks, Bryn. Just a quick piece here. You're looking for information about the Next Generation Science Standards. You want to pop to the NSTA website. You can find a link to it on our homepage, or just remember nsta.org/NGSS will get you there. As we've gone through our series, I want to mention we've got one more coming up. All of our web seminars take place on Tuesdays from 6:30 to 8 Eastern Time. Next week, 2 weeks from today, we'll be doing Obtaining, Evaluating, and Communicating Information with Phil Bell, Leah Bricker, and Katie Van Horn, who will provide some information here about that. I hope to see a bunch of you, especially those of you who've made it 7 for 7 so far. We want to run the table. I do also want to point out that, again, we're going to be having some more web seminars starting up after the first of the year. As you know, there were some opportunities to gain some graduate credit for these web seminars if you attend all or view the recordings from Shippensburg University, and you can find some more information about that on the web seminar information page. We do have a community forum in our Learning Center on the Next Generation Science Standards. Also wanted to note here, for those of you who are NSTA members, we have a members-only listserv now that is focusing specifically on the Next Generation Science Standards, and you can find some more information on that under social networking on the NSTA website. That just opened up this week. And for those of you who are going to Phoenix, I hope to see some of you there. I'll be doing some sessions at the conference, as will Joe, actually, doing a 2-hour session, I think, on Thursday afternoon at the Phoenix conference, focusing on modeling. And so please look to do that. We'll provide some more information down the road soon about a huge number of opportunities at our San Antonio conference next April around NGSS. Again, we've mentioned the framework a number of different points here and how you can get that. There's also a reader's guide that NSTA prepared that I would recommend for you that I think is also freely available. And in our journals, we've been doing a number of different articles. Joe's written one for us, I know, about the framework and the standards. And so with that, just want to thank Joe and turn things over to Bryn for the administering the survey.
Thank you, Ted, and I would like to thank you and Joe Krajcik for your time this evening. It was a great presentation and lots to take back to the classroom. Wonderful to have everyone's participation as well. And we would like to thank the sponsor of today's web seminar, the Carnegie Corporation of New York. Also a thank you to the administration of NSTA for their support for web seminars. And here's a look at our upcoming web seminar calendar. Tomorrow you can join us with the American Chemical Society to look at physical changes, chemical changes, and how to tell the difference. Then on Thursday, join us for a program in our NASA Explorer School series and take a look at an engineering design challenge, thermal protection system. Then next week on December 11th, look at giving yourself credit, planning your professional learning activities, and that will feature Flavio Mendez, NSTA's Senior Director of the NSTA Learning Center. You can register by going to learningcenter.nsta.org/webseminars. I'd like to thank everyone for your participation and look forward to seeing you again on another NSTA web seminar.